All right, let's get started. You turn it in up here. I'm looking for my towel, rag, nasty thing. Make sure it's stapled or paper clipped, one or the other. Okay. Oh, thank you. Where was it? Okay, thank you. Oh, there's one here too. Okay, I'm going to pass back the other ones, but I'm going to do that when we take our break. I'll pass it back. But I will mention that I know a couple of you are concerned about the grade on the first one. So let me just say this. The first one was kind of a feeling out process, I guess, for you to kind of see what to expect. So remember, the intention of these things is for you to ask questions. Like you should have some issues with them. I mean, that's kind of my hope, is that they make you think a little bit more than you do in the homework at least. And so don't assume, like if you have a question of whether or not you're doing it right, like just run it by me, because it's better to ask a question and me say, yeah, you're doing it the right way, than to do it wrong and then wind up getting points taken off, because you only get four of these. Like there was the one on the first test about the regular pentagon, and I asked for the dot product. Some people just did it visually, like just drew the vector, the dot product, instead of actually calculating like the exact value of the dot product. So that obviously is way off. So just ask questions. So if you didn't do well on the first one, then I will allow you to do another one, and then I'll figure out how I can maybe average the grades or weight them or something like that, okay? But just for that first one, because you've been thoroughly warned now, you need to ask questions, all right? All right, so everyone that's turning in the second one has turned in? Anyone else? All right. We have an exam on Monday, right? I will talk about that exam towards the end of class. What I'll do is I will just kind of verbally tell you the types of questions that I've asked on past exams for this class. I'll just say, I'm going to bring it up here and look at it. You won't look at it, but I'll look at it and I'll just say, oh, I asked them to do this, 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 and it'll give you some feel for what to expect. But remember, I said focus on your homework, right? Okay, so what are we doing today? We are doing maximum and minimums. So we finally have, I think, gotten to a point where we're going to do some stuff that I think seems applicable to real problems. So this is the section 11, chapter 11, section 7. There's only one more section left in this chapter, and this section will be on the test. All right? So where do we begin? We begin back in Cal 1. So I have an example here I'm going to show you. Let's see if it's still here. Have you ever heard of this website called Desmos? It's a pretty cool website. You can type in functions and it will graph them for you and stuff. So I had this website take a look at the function f of x equals x cubed minus 4x plus 1. And in Cal 1, we learn how we can find the local maximums and local minimums of this function. And we also talk about finding the absolute max and mins on closed intervals. So there's kind of like two different approaches in Cal 1. The closed interval method, and then there's the method where you're not on a closed interval. So I'm going to start with the closed interval method. Let's say I take this and I restrict it to the interval -3 to 2, all right? Then this is the graph of it here. Can you all see that okay? Everyone see that? Okay, so it starts here, goes up, down, and then ends here. And in Cal 1, to find the absolute max and min, do y'all remember what y'all did? To find the highest and lowest points of that graph, what did we do?
We got the edges and we got the inflection.
Yeah, so you figure out what's happening at the endpoints, right? And then you compare that to what's happening wherever the derivative is 0 or undefined, right? So you found these things called critical points. Critical points are critical numbers. Depending on the textbook, they're called different things. So to find these critical points, what we did is we take the first derivative, we set it to 0. Then we also figure out where the first derivative doesn't exist or where it's undefined. Anywhere where these things happen, we might have max and mins happening there. So we take these, we figure out the critical points, and then what we do is we evaluate the function. Let's go ahead and find it because it's not too hard to take this derivative. The derivative of this function is 3x squared minus 4, right? And if I set that equal to 0, then let's see, what do we get? Yeah, 3x squared minus 4. So we set that to 0, we get 3x squared equals 4. So x squared is 4/3. So we get x is equal to plus or minus, take the root on top and bottom, 2 over root 3, right? And so what we do is we say, okay, we have two critical numbers or two critical points so far. Then we check, is the derivative ever undefined? And it's not, right? It's always defined, so we're good. So what we do is we check these two. We make sure that they're in this interval. Okay, so we make sure that those two critical numbers are in here, and they are in this case. So then we take those and we take these and we evaluate the original function. We say, okay, what's the original function at -3? What's the original function at 2? What's the original function at both of those values? And whatever these outputs are, we compare them, and the biggest one is our absolute max and the smallest is our absolute min, right? Yeah. Okay. So that's how we do the closed interval method to find the absolute max and absolute min. What's great about technology is that if you put this into Desmos, right, and then you just you type it in, you can restrict the domain, and then you can just hover over. You can figure out what these values are. You can go to the endpoint here. See 2, 1. You can come down to this endpoint. So I could do all that calculus that I just did over here. I can just do it just by typing it in the computer and hovering my mouse over, right? So very convenient, right? Okay. If I don't want to do the closed interval method, and instead I want to just open up the domain, now I'm looking at this graph, and it extends in both directions forever. So our method changes, and we can't find absolute max and mins anymore. We can only find local maxes and mins. All right? And the way we do that is a little different. Do you remember how we do that if we have a non-closed interval? So we do the same thing. We find the critical numbers. I'll say CP for critical points, right? We already know that those were plus or minus, 2 over root 3, right? So there's kind of two ways to do it at this point. One way is to do a number line, plot your 2 points, and then some of you learned this. I know most of you didn't learn it the way I teach it, like sine tables. Sine tables? No? Okay, I don't do sine tables, but you're basically going to look and see, you're going to take test points and plug those into the derivative to see if your function is going up or down. And so what you're looking for is in this case, it looks like it would go up here, then down, and then down, then up. So you would know right here you have a local maximum, and here you have a local minimum. This look familiar? And then there's also this thing called the second derivative test. The second derivative test says, if we take the second derivative of this function, which is what? What's the second derivative of this function? It was 3x squared minus 4, so it's just 6x, right? Yeah. If we take that and what do we do here? We go to these critical numbers, right? Do y'all know? Have y'all seen this? Yeah. Okay, so you find these, then you find your second derivative, and what do you do with the second derivative?
You just plug it into this polynomial.
you plug in these, right, and see if they're positive or negative here. So the idea is this. Right now, I know that at, let's go to positive root 3 over 2. Here's what I know. At this point, which I don't know what the graph is, but here's what I can tell you. The slope of the tangent line is 0 there, right? Because the first derivative was 0 there. Then I look at the second derivative at that point. And if I plug in positive 2 over root 3 into here, I get a positive number, which means I'm concave up. So if you have a slope that's 0 and you're concave up here, then you have to have a local minimum there. And if it were concave down, then it would be a local max. All right? That's your second derivative test. But again, closed interval, absolute max and min are possible. Open intervals, you can only talk about what's happening locally, right? All right, and what's really nice about this, having this technology, it's almost sad because you can do almost everything you do in Cal 1, you can do it without doing any calculus at all. Like right now, if I asked you to find the local maxes and mins of this by hand, this would be a disaster, right? This would be an absolute disaster. To take the derivative of that and set it equal to 0 would be extremely difficult. But with technology, I can just come here, plop, boom, there's the graph, and I can see, oh wait, let me click on it, there we go. I can tell you I have a local minimum right there. Looks like I have a little local max right there, right? Doesn't it look like a little local max there, another local max here. I can zoom out, look for anything else. I could have zoomed in, right? I could take a look at my x-intercepts. Ah, no. There we go. I could find the x-intercepts. Look at that, beautiful, right? Okay, so with all this technology, it's great. But now what we want to do is we want to take a look at a surface, right? So this three-dimensional surface. And we want to talk about how we would find the maxes and mins of something like that. And unfortunately, technology is not to that point yet. Okay, we cannot go, unless somebody knows of something that's come out that I'm not aware of, where you can just go to a website, type in a function of 2 variables, and it graphs the surface and gives you the max and mins. Anyone aware of anything like that? I mean, you can do it within a program as long as you know how the program works and you code it up yourself. But in terms of just going to a website, we're not there, right? So that means we still have to do it by hand. That's what today is about, all right? So do you all remember on these, with the problem I gave you, the closed interval and then the non-closed, do you remember which one is taught first? Do you remember which one you learned first? Did you learn the closed one first, or did you learn the non-closed one first? Closed. Usually it's closed. Most textbooks do closed first. And that's because it's easier to do, because all you're doing is finding critical numbers, plugging in endpoints, plugging in critical numbers, comparing, no big deal, right? So we are now going to take a look at surfaces, trying to find the max and mins. So the first part of this is I was supposed to review Cal 1, which I've already done, okay? So here's some examples of surfaces. So there's a surface. This one is kind of interesting, right? And we are looking for possibly how we might be able to go about finding these little high points and these valleys, right? The low points. Here's another picture of the same thing, okay? Right, so how do we get those points? Now, we have some names for these first. You know, if you have a surface like this one right here, this is straight out of the textbook. It looks terrible. That's, I think, a better picture. This right here, these points right here would be local maximums. You know, you have like the point that's the highest locally. These are local maximums. This would be your global maximum or absolute maximum, the highest point on the function. And then same thing for the bottom. You would have minimums, right? You have, let's see what the minimums look like down here. Looks like we've got a couple of minimums there, right? Local minimums, global or absolute minimum there. So that's just the same sort of terminology that we had from Cal 1. And that's what this goes on to talk about and blah, blah, blah. All right? So unfortunately, there's not an easy way to prove to you why what I'm about to show you works. You know, a second ago I said, look, we go to a point, the derivative is 0. The first derivative is 0 there, and the second derivative is positive. We know that we're concave up, flat, so we know it's a local min. I think visually you can kind of agree with that, right? First derivative 0, second derivative greater than 0, we have a local min. I'm about to show you something on how to find the local max and mins of these. It's not going to be as easy for me to convince you why it is the way it is, all right? The proof of it is very challenging, and actually it's beyond the scope of this class, all right? So you're just going to have to take this and just go with it, okay? All right, so our first note here is this. We are trying to finding the local max and min of a function z equals function of two variables. So that's where we're going to start. We're going to start this by looking at a surface and trying to find its local maximums and minimums. This is backwards from Cal 1. Cal 1, we closed the interval, right? And we found absolute max and min. And then we did, non-closed. Here we're starting with non-closed intervals. And we're just going to let whatever the domain of the function is, and we are going to be trying to find the local max and mins, all right? And the way you do it is this. There is a thing that they call the second derivative test for surfaces. And I might be able to zoom this in here for you. So what you're going to be doing to run this test is you're going to be calculating this thing called capital D. But let me get to that. So the first step is this. First step to finding the local max and mins is this. We are going to find what we're going to call the critical numbers, or critical points. So what was that in Cal 1? It was wherever the first derivative was 0 or undefined. Here, in this setting, the critical points are anywhere. This is any point, any point AB such that the partial of f with respect to x at that point is 0, and we also need that the partial of f with respect to y at that point is 0. So it's very much like the finding the critical numbers for Cal 1. You set the derivative equal to 0. Well, here we are going to have to set the first partials, both of them, equal to 0. And so what we're really doing is, I was thinking about this last night. I couldn't sleep because my dog woke me up, and it was okay. So I couldn't sleep, and I was sitting there. Do y'all get it when I'm standing here, like going in class and like doing this? And do y'all see it or not? I mean, what? Like when I'm going, go this way and then go that way, and then you're up here and you're doing that. Like, do you see it? You don't see it?
I see something. I'm not sure. I'm not sure if I understand that stuff. I understand what you're saying.
So you said no. You said no.
I understand.
This is like I'm standing on this thing, right? Somewhere, right?
Yeah.
So like I'm in the domain. I'm on the ground. I'm walking out to an x. I'm walking out to a y. That's my input, and then that gets sent up through the function into the surface somewhere. Now I'm standing here, right? So I'm standing here. If I'm trying to find the point where I'm trying to find points where I stand where these first partials are equal to 0. Means that I'm trying to figure out where I need to stand so that when I walk in that direction, my tangent line is flat, right? And then when I walk in that direction, which is this one, my tangent line is flat. That's my starting point. If I'm flat in that direction, I might be at a local max or min, okay? I might be. It's not guaranteed. In Cal 1, same thing. It's just because your derivative is 0 doesn't mean you're at a max or min, right? What's your derivative right there? 0, is that a max, a local max or min? No, right? Same story here. Just because the partials are 0 isn't enough. But that's where we start. We say, first, let's find these things called critical points. then the next step is we're going to calculate this thing called capital D. All right? And this is our second derivative test. And here's what capital D is. And I'm going to write it out. I'm going to write it on the side over here so I can refer back to it. So capital D, which we will have to actually calculate capital D at every single critical point we find. So we might find multiple critical points over here. And then for each critical point, we have to calculate this thing called capital D, which is the second partial with respect to x of our function at that point times the second partial with respect to y at that point minus the partial with respect to x followed by y at that point, that quantity squared. And this right here is going to be a number. All right? That is going to be a number, D. Once we calculate that answer, so this is similar to the part where in Cal 1 where you looked at the second derivative, positive was concave up, negative was concave down. That's what we're doing right now. But positive and negative doesn't tell us the answer. We have 3 different scenarios. There's actually 4 scenarios. They didn't put it here in the book, but I'll put it here. First of all, if the D that we calculate is positive, then we might have a local minimum. If D is positive, we might have a local maximum. Okay, so the first thing we do is we look at D. If it's positive, maybe there's a local max, maybe there's a local min. If it's negative, we don't have a local max min. So if D is negative, automatically we're done. We don't have a local max min. Got it? But if D is positive, then we have to resort back and then look at this piece right here. Okay? Which means we have to go and look at that right there. Okay? This one piece. If that piece is positive, what do we have? We have a local minimum. Okay? And if that's negative, we have a local max. So that's kind of like that second derivative part. Positive be local min, negative would be local max. But to run this test, you first have to have that your D was positive. All right? So what case is missing here that the book doesn't mention, at least not in this note? Yeah, what if D is 0? If D is 0, test fails. The test fails. Which means you don't know yet. You still don't know. Okay? You still don't know what's happening. All right. Just kind of, at least the framework of this makes sense. We're going to start looking at some functions, and we're going to start to try and find local maxes and mins now. So now we get to actually do the mechanical part of this. And I thought, before class, I was thinking maybe I can try and prove this, like explain why this is true. And I started to look at some proofs and trying to find something that might be worth our time. And I figured it was going to take at least half an hour to get through it. And I just said no. Okay, so we are just going to take it and move on. So here we go. Here's our first example. Find the extreme values. That means find any local maximums or minimums. That's what this means. Of this function of 2 variables. All right, you ready? First step, critical points, right?
Yes.
The second step was the calculation of D. I don't think I put step 2 earlier. Who cares? Critical points. There might be one, there might be more than one. Let's see. So to do this, I'm going to need these partials set equal to 0, the first partials. So what's the partial of f with respect to x? Negative 2x. Okay, and then what's the partial of f with respect to y? 2y. Okay, so what we need to find now is we need to see, can we find a point AB such that the partial of f with respect to x at that point equals 0, and the partial of f with respect to y at that point equals 0. So can we find this or not? Well, There's only one way to make this 0, right? The only way we can make the partial of f with respect to x equals 0, that's negative 2x equals 0, is if x is 0, right? We know that for sure. And the same thing for the second one, right? So the only way to make this one 0 is to make 2y equal to 0, and that forces y to be 0. So we have to make these both 0 at the same time, right? So what would be our critical point? CP for critical point here. What is it? 0, 0, right? That's it, x0, y0. We only have one critical point. It's the point 0, 0. There's no other way to make both of these 0 simultaneously. Okay, so there's only one critical point. So now what do we do with it? Calculate capital D. All right, so let's calculate capital D. So when we calculate capital D, this is step 2. We're only going to be looking at capital D at the point 0, 0, right? All right, well, to do capital D, don't we need second partials? So maybe we should do the mechanics of that before we start calculating D. Maybe I should have done that at the beginning, but I didn't. So let me go ahead and do that now. What is the partial of f with respect to x twice? So that's this one, right? Hit it again with the derivative, negative 2. What's the partial of f with respect to y twice? Positive 2. And what is the partial of f with respect to x then y? So that's this one right there, but with respect to y now. So that's 0, right? So that's 0. So for this D, do y'all notice for this D that these pieces are completely independent of my critical point? Like my critical point has nothing to do with what's going to happen with D for this particular example. D is the partial of f with respect to x twice at 0, 0, but it's a constant. So there's only one thing it can be, negative 2. And then this second piece is 2. And then minus that piece squared, so 0 squared. And that gives you negative 4, right? Yes. And that means negative 4D is less than 0. And right there, you can say that there are no local maxes and mins, right? So anytime this happens, what we have here is what we call a saddle point. Okay, we have a saddle point whenever D is less than 0. And you can tell, I think, from the picture, right? The origin right there, that's the point 0, 0, where something interesting is happening there. But what's happening? You have a saddle point. Because it looks like a saddle, I guess. I don't ride horses, but I imagine that's what a saddle would kind of look like, right? All right. All right, that was the first example, the cleanest, like straightforward, right? Okay, so yeah, let's see something a little bit worse. And these are just going to get progressively a little harder. And then it's going to start to come down to algebra. Like we're gonna make sure that, well, you've only gotten through, you know, college level algebra and pre-cal and cal 1 and cal 2, so I think everyone's algebra in here is probably decent, yeah? On the side of good. Great. Exceptional. All right, let's go. First thing is critical numbers, right? Critical points. So to find my critical points, I need my first partial with respect to x. Let's go ahead and get that, and then partial with respect to y. So what's partial of f with respect to x? 4x cubed minus 4y. So what happens if you can't get your partials right? I mean, you're kind of dead in the water then, right? Pretty much. So take your time on those, because the rest of the problem is based on this, right? All right, so now 4y cubed minus 4x, okay? Now, should we get the other partials that we need for D? Do y'all want to just do them now? It's totally up to you. The only, I guess, drawback to that would be, what if you get to this and there's like no solutions? Then you've wasted time doing calculations, right? When you're never going to get to D. But that's not going to really happen. So not with anything I'm going to ask you. So let's go ahead and just get them now. Partial of f with respect to x twice. 12x squared. Okay, see how this second partial does depend on x. So this will not be a constant in the calculation of D. Partial of f with respect to y twice, 12y squared. And then what is the partial of f with respect to x, then y? So that one with respect to y. -4? So that one is a constant, right? That one is a constant. But that's still not enough to know what D is, because I got to know what these turn out to be. Although I do know both of these are positive, right? So I know that both of these are going to be positive, but the thing is, I don't know how big this is going to be. Because when I put that in there, it's going to be like -16, right? When I squared -4. So if these turn out to be smaller than 16, then I'm going to have a negative. If they turn out bigger than 16, it's going to be positive. But so there's still a lot of work to do, all right? Okay, so that's me just getting all the derivatives ready to go. And now let's go ahead and find the critical points. Let's figure out where that is 0. Okay, what's wrong with that, though? If you're trying to set that first partial equal to 0, you have a single equation, right? And you have two unknowns. You're not going to be able to solve that for any particular value, right? You're not going to be like x is 2 or x is 0, right? Because you have y in there also. And the other equation works the same way, right? Partial of f with respect to y is equal to 0, means that you have to set 4y cubed minus 4x equal to 0. So anyone have any suggestions? You just said, I asked and everyone raised their hand, said that they were great at algebra. So any ideas on how to go about this? Go ahead.
Call me crazy, but how would we put them equal to each other?
You can set them equal to each other, can't you? Right? They're both equal to 0. They both have to be equal to 0, so why not set them equal to one another? Yeah. That is a method we can use. You want to go for it? Let's go for it. Now, there's another way to do this, but let's just go with that. So now I'm going to set 4x cubed minus 4y equal to 4y cubed minus 4x. Now, we still have a single equation, though, right? We still have a single equation that is got two variables in it. But I don't know, maybe we can do something with it. So what now? I'm just going to follow your lead, even if it goes off the edge of a cliff.
My lead.
Whoever, well, if you want to continue, you can. This was your idea. Let's just remember that. This was your idea. Whatever happens.
Thanks. Thanks for shuffling responsibility.
Hey.
Like a true pro. I'd say.
Oh no, you don't have to keep going.
Oh.
I'm asking anyone to do this, but we will blame it on you later if we can't, if we get stuck.
It's okay.
Okay. How about this?
Yeah.
Okay, let's just get rid of those 4s because they're just in the way. Okay, now what?
Set y x equal to each other on separate sides.
Set them. Let me help. Okay, do y'all agree with that? First two terms. First two terms are a difference of cubes,
Yes.
right?
Right.
So they factor. Those factor. And I'm doing this because I realize that this factorization is x minus y, x squared plus xy plus y squared. That's the difference of cubes formula here. And the x minus y is nice because I had an x minus y here also. Do y'all see that? And so now you can factor out an x minus y. So if I factor out x minus y, then what will be left here? I don't need brackets, but I'm doing that to just really stress that I pulled x minus y out of both of these.
It'll
So
be x squared plus xy plus y squared plus 1.
equals 0, right? Yes? Now we have factored. And since we have factored and turned this into multiplication, that means I can set each of those equal to 0, right?
Yes.
So one thing I could set equal to 0 is x minus y equal to 0. And then the other thing I have to set equal to 0 is x squared plus xy plus y squared plus 1 equal to 0, right? That's what I'd have to do. All right. The one on the left looks doable, right? This one?
Yeah.
That means that what would have to be true?
X and y the same.
Right, x would have to be y. Okay, now this one, not so obvious. In fact, we know, hopefully you know, that when you do a difference of cubes formula, this right here will not factor. Like, will never factor. Not over the real numbers, because just imagine, if this did factor, then they would have given you a different formula that has it factored more. This guaranteed won't factor. So, yeah, maybe we just back burner that one for a minute, because this is kind of problematic. Do y'all agree that's kind of problematic? But I do know this much. In order for me to have these two equal one another, I would have to have x is equal to y. They'd have to be the same value. So now what we can do is we can go back to either one of these and replace our y's with x's or our x's with y's. So let's do that. Keep going here. I'm going to continue right here. So I'm continuing this thought right here, that if I go to this equation, let's take this one, and rewrite it like that, now I can solve that for x. Pull out a 4x, x squared minus 1 equals 0. Wait, hold on, is that right? Yes. Yes? So x must be 0 or 1 or negative 1. There we go. So we set that to 0, we factor that again, or square root both sides, however you want to do that, and you get those three answers, right? And remember, x had to be y, right? Remember, x had to be y. So if these are my x's, then what are the critical points that I get from this then? 0, 0 is one critical point, 1, 1, and lastly, negative 1, negative 1. But we still have not dealt with this. So how are we going to deal with that? Any ideas? I mean, I have three critical points right now, right? I could go calculate D for each of those, but is that everything? That's kind of, you know, what's missing? Are there solutions here or not? So does anyone have a way to solve that?
X plus y squared, right? 1b squared.
Where's that? We're missing a 2 here. We need a 2 right there, right? If that was 2xy, then we could do x plus y quantity squared. And that would be real nice because that plus 1 would never be 0 because we'd have a positive plus 1. Can't be 0. So, since this is not something easy to do, what I would do is I would have rethought how I approached it to begin. Because this is difficult. So I feel good I've got some answers, but I'm not sure if I have them all. So I'm going to go back and not start over, because I mean, I don't want us to feel like that was all a waste of time. Thank you very much. It wasn't a waste of time. But maybe there's another way that we could do this. So, I mean, if you have two equations and two unknowns, when they're linear, you usually solve one for x or solve one for y and then plug it into the other, right? Yeah. We can do that here too. It's just they're non-linear. So why don't we solve this one for y? Okay? So let's solve the first one for y. What would we get? y equals x cubed. Okay? So I'm taking that one, solve for y. Okay, and now you take that and plug it into this equation. You replace y with x cubed. So you get 4x cubed cubed, right, minus 4x equals 0. So that's your second equation plugged in. And this is going to be 4x to the 9th minus 4x equals 0. And then you can play the same game and factor, right? So 4x comes out. You're left with x to the 8th minus 1 equals 0. Y'all following me? Now this is one answer, right? X is 0. This can be factored again. X to the 4th minus 1, x to the 4th plus 1. Difference of squares, right? I'll just keep going. This one cannot be factored, but this one can, right? Again, so this is 4x, x squared plus 1, x squared minus 1. And then this one can't be factored. You can't factor a sum of squares, right? Can't do that. But then that one goes again, x plus 1, x minus 1. So we're going to get 0, plus 1, and minus 1, which is what we had before. But now we don't have that weird quadratic sitting out there that we were worried about. And so you could actually conclude right now that that quadratic that we were looking at has no real solutions. We know it because then this would have had other solutions. So the reason I didn't stop you from doing that is because there are problems where setting equal to 0 is actually the better way to go. This is a problem where that wasn't necessarily better. Got it? Okay. So from this, we have, let's see, our solutions here are, let's get our solutions. Our solutions here are x is 0, x is 1, and x is negative 1. Now, x is not y now, right? X is not y. This is our relationship. So now to get our y's, we do 0 cubed, 1 cubed, negative 1 cubed, which gives us the same answers. But I just want you to know it's not the same. We're not solving it the same way, so we don't have the same relationships. All right, so 0, 0, 1, 1, and negative 1, negative 1. There we go. All right. It's D time. All right, so let's do D. Let's start at 0, 0. Okay, so we're doing this. So we're doing the second partial with respect to x, right, twice. And we're going to be replacing that x with 0, right? So that's going to give us just 0 for that first piece. Times, what about that second piece? We're going to be going into this right here with y being 0, and that's going to give us 0 again. And then we have minus, and then we have the negative 4 being squared. So at the end of this, we get negative 16. Right? Which tells us we have what? Saddle point. We have a saddle point at, now watch what I do here. A saddle point at 0, 0, 1. Okay, so what did I do there? Why did I put 3 numbers in there? Yeah, so now I'm actually, like, I know that when I plug in 0 for x and y and go up to the surface, I know that at that point I have a saddle point. But it would be useful for us to know where we are on the surface. So take 0, 0 and plug it into the original function, 0, 0, 0, you just get the 1. So that gives us the x, y, and z. So it tells me exactly where I am on the surface. Okay? Next. Calculate d at, let's go with 1, 1. All right, so we basically always are going to have 3 pieces to this, right? And can I just put minus 16 for this one because it's going to be the same thing? Yeah. Okay, so what's happening at 1, 1? What do we get here? 12. Here? 12 again. And then when you do that, that's bigger than 0, isn't it? Okay, so that is positive. Since it's positive, I now know I either have a local max or a local min. I now need to look at what piece? This piece right here. If that's positive, then that's like the concave up, right? It's a local minimum. Okay? So because this is positive, we know that we have a local min at, and let's write it out as an ordered triple. 1, 1, and then 1's into there. So -1, right? 1, 1, that's 1, that's 3. Yeah, -1. No one's agreeing with me. What's wrong? Okay. Into here. 1, 1, and then 1, 1, -4, plus 1. So 3 minus 4. Yeah? Okay. What about the last calculation for D? D at -1, -1. So this will be 3 pieces here, minus 16 again. So is there any difference? No. There's no difference. Because of our partials over there, they're squared. We're going to get the same thing here, 12, 12, right? And so when we go in here, we get, oh, we don't need that. So we get a local min again, because this thing is greater than 0, right? Greater than 0, and that piece right there is positive. Yeah. Do we get the same z coordinate? If we go -1, -1, what do we get there? So -1 in here would be +1, +1. Negative and negative is still going to be positive, so that'll give you -4. Yeah, same value. What was it? -1? There we go. Shall we take a look at the surface? Okay, I think I have it down here somewhere. There it is. Oh, let me erase this. We should have a saddle point at 0, 0. And then we should have 2 local minimums. And I'm going to pull the surface out so you can kind of see through it a little bit. See the saddle in the middle? Okay. So the first example that we did, very straightforward algebra. Second example, algebra was a little bit messier. Let's see what happens here. Okay, so partial of f with respect to x is 3x squared y plus 24x, right? Partial of f with respect to y, x cubed minus 8. Let's go ahead and get the other partials. With respect to x twice, 6xy plus 24, partial with respect to y twice. 0, right? Partial of that with respect to y, there are no y's. It's all constants, so derivative 0. Partial with respect to x followed by y. So that's this one, but now with respect to y. 3x squared. All right. Let's find those critical numbers or critical points. So we need to figure out where this partial 0, which means I need to set 3x squared y plus 24x equal to 0. I look at that, I see one equation, I see 2 unknowns. So I know I don't have nice solutions right off the bat, right? But when I look at the second one that I have to satisfy, this one is x cubed minus 8 equals 0, and that I can solve easily. Is there a question? Or is there something off? No. You sure? No. sure? Okay. See, I'm going to go after this one first. This one has one unique solution, right? 2. So if x is 2, that is the only way to satisfy this, right? The only way this one is true is if x is 2. So if x has to be 2 here, then it has to be 2 there also, right? So now what I do is I go back to this equation. I replace x with 2, so I get 3 times 2 squared y plus 24 times 2, which is 0, has to be equal to 0. 4, 3, 12. 12y plus 48 is 0, which means y is equal to negative 4. Y is negative 4. So I only have one critical point here, right? That's it. So my critical point is the point 2, negative 4. So I only have to calculate d for that point. That's kind of nice, right? That algebra was a little easier than the last one, I think.
Yeah.
So long as you go after this one first, right? Go after that one first, then you're okay. All right, let's do d. I'll leave that up on the board. Let's do d at 2, negative 4. So I've got some pieces here. All right, we need the partial of f with respect to x twice. That's this one. Plugging in 2 for x and negative 4 for y. Let me just do that in red, since we only have one of these to do. Right, 6 times 2 times negative 4 and plus 24. That's what I get when I plug in 2, negative 4. And what is that?
It's going to be negative 48 plus 24.
Yeah, so negative 24? Yeah. Negative 24 here. And then it's 0 here. Oh, well, shoot, I could have concluded this a long time ago then. What is this one? Well, unless it's 0, unless the whole thing's 0, right? Okay, so what's this last piece here? So we plug in just 2, right? So 12, so this is 12. So this thing turns out to be less than 0, right? A negative number, which means we just have a saddle.
Yeah.
That's it. So we have a saddle point at 2, negative 4, and then we plug those into that, right? Which I'm not going to do because I already did it. When you plug it in, you get 48. So here's a picture of it. Kind of a cool looking function, if you ask me. It's kind of a weird shape, isn't it?
Looks like the weirdest water slide in existence.
Okay. Oh, that is E raised to that, right? Yes, it is. Yes. Yeah.
Could you have inferred from the very beginning, since like you knew that fyy was 0, and you knew that the function of xy was a squared function, so you knew that was always going to be positive?
Unless this was 0.
Unless it was 0.
Yeah. So the critical point, we needed to know what it was because we knew what the second partial was, right? What was this partial? I forget.
That was 3x squared.
3x squared. So we would have had to have just made sure that x wasn't 0. Then we could have concluded that this should be negative. Yeah. Yeah. Okay. Yeah, don't keep that. Are you catching on to this? Right. Why don't you take the next, I don't know, say 10 minutes, see if you can get this one. Okay? And I'll let you go after, let's see, it's 2:55 and go till 3:05 and see what happens.